causes a lot of problems because we may have one image like this, which you can see is all aggregate and hardly any paste, and another image right next to it where we've got mostly paste and hardly any aggregates. And if we just measured the amount of remaining cement here and the amount of remaining cement here, we get something which is rather nonsense because we get very different answers in the two cases. So what we want to do is to put everything on an even basis, and we do that by taking out the aggregates. So there's the aggregates, and then we subtract those out, and we can get a degree of reaction that's roughly the same in the two cases. I think it's better illustrated here. So here we see 4 images from the same sample. We also see another part of the problem, that in most cases our aggregates don't just have one grey level, they have several grey levels. They may contain 3 or 4 different mineral phases. This makes it a little bit complicated, but it can be done. We can then take this aggregate here, this color aggregate here, combine them to clean them up, combine them together, and quite effectively eliminate the aggregates. So here's the 4 different images. Here's the extraction of the aggregates from all of them, and then we can measure the amount of unreacted cement quite effectively on the basis of the paste phase. So that works quite well, and I mean the important point is like all of this can be automated. So you can have standard routines, you can put your sample in your microscope, you can collect say 200 images, which is typically what you need to get a good representative analysis. It takes about 2 hours or so to collect the images, and then you can analyze these offline, and it can all be done really fairly quickly and routinely. The other thing you can do, you can really get an idea what's happening over a whole sample. So this is an example where we wanted to look at gradients occurring in this thin layer of mortar. This is the kind of mortar that's used in various kind of applications where you put a thin layer of mortar on the surface of bricks, for example. And to do this, you can automate your microscope, so your microscope collects these images one by one. So here there's about 200 images, and then you can join them all together, and when you've joined them all together you can't see where they're joined, which is very nice. But the important thing is in each individual image you've got a very good resolution. You can analyze quite easily your sand, your unreacted cement. You can see that this is a very porous material. This is quite typical of these kind of applications where you have thin surfaces on the outside of a building. They're actually very, very porous materials. And by looking at different ones here, we can see in the different cases, we can segment the different phases, and we can see how the amounts of those phases vary as we go through the sample. So this was 4 kind of blend with different kind of lattices in. You can see what's typical is you get this edge effect. At the edge, the material's drying out, and it's not reacting so much. Another thing you can do is you can get an idea about density. I talked about this earlier when we were talking about effective hydration temperature. And clearly, you can't just go on impressions, not least each time you put a sample into the microscope, the absolute grey levels will be slightly different from one sample to another. So in order to get a quantitative analysis of what really is the grey level of a different phase, you have to calibrate it to things you know about. And in this example here, we use the calibration relative to 2 things which has a pretty fixed density. One was the alite phase here, and the other was the calcium hydroxide here. So I said it was difficult to extract calcium hydroxide, but the peak you get from calcium hydroxide is very reproducible. And by measuring this distance here and this distance here, and then the ratio of one to the other, you can get a very reproducible fix for what is the position of this CSH peak here. And this is this micrograph I showed you earlier from a paste that was cured at 2 different temperatures. This is the histogram. I mean, this is a very kind of obvious case. You see the two different CSHs even produce different peaks like this, and by applying this technique, we can get a precise quantitative measure. What's the relative density of one CSH compared to the other? So finally in this section, we're going to look at, anybody any questions about backscattered images? In the reading, there's a quite detailed paper I wrote a few years ago all about backscattered electron imaging and what it can do. And if you want to know any more, I think you should find most of the answers there. So finally, we come to characteristic X-rays. The idea of this is that you have an electron coming in, which knocks out an inner shell electron, and then you have another electron which falls into that inner shell. And because of the quantization of energy of electrons, the X-ray which is emitted as the difference in these energy levels is characteristic of the element that's present. So if we just run that simulation again, you see the electron comes in, knocks that atom out, this electron out, this electron falls down, and you get the X-ray given off. So typically you'll see a spectra like this according to the energy, and this is the most common method you use, that you have an equivalence between the energy of an electron and its wavelength. The quickest detection method is to use this energy dispersive spectroscopy, and here you can go right across. You can see a peak for the silicon here and the calcium here. So this is a spectra for C3s, this is a spectra for C3a, and in this way we can get exactly what are the compositions of these different minerals. Again, the problem is this intermixing. So, if you see these random points here, you can see this point is coming from mainly from CSH, but with a lot of other things. That's the case. That's true for all these points here. They're analyzing a volume about this size, and this volume can contain intermix several different phases. So this is why we make these kind of plots, which I showed you earlier. And usually we'll see this kind of distribution. We'll see a cluster here, and this cluster here corresponds to the calcium silicate hydrate. And then these points spreading along these axes here are points which are intermixed with calcium hydroxide, points which are intermixed with yttriumite or monosulfate. And we can better distinguish yttriumite from monosulfate on this kind of plot here, where we plot sulfur calcium to aluminium calcium. And we can see how these evolve with time. I already showed you these plots here. You can also use this in a kind of mapping mode. So this is a typical example of mapping. And it's not, to be quite honest, all that useful here, because here we see a grain. We can see there was ferrite phase here, and you can see that ferrite phase shows up very clearly in this iron map here. Well, we knew it was ferrite phase before we started, so we didn't, it's a nice pretty picture, but we didn't actually learn that much from it. Here we can see the distribution of alumina. Alumina is in the ferrite phase, but it's higher in the C3a phase, and so on and so forth. This is much more useful when you want to look at a kind of degradation reaction. For example, you want to look at sulfur coming into a sample, or calcium being leached out of a sample. So the summary about scanning electron microscopy. The big advantages is you can qualitatively identify the phases. You can do this in several ways. You can do this by their morphology in secondary electron. You can do this by their gray level in backscattered electron. And you can do this by the chemical content by energy dispersive spectroscopy. You can more precisely determine the composition by energy dispersive spectroscopy. You can look at morphology by secondary electron, backscattered electron. You can then quantify things in backscattered electrons, you can look at distributions, you can look at elemental distribution, and many, many more things. And often, because you've got these nicely automated samples, people tend to actually forget to look at their samples. And quite honestly, it's most important to sit down and look at a sample, look first of all at low magnification and then at higher magnifications before you start doing these analyses. The real drawback is the specimen preparation. As I've said, you've really got to dry your sample. Even if you're in an environmental microscope, you're still drying your sample. You've got to support your sample with resin, and you've got to polish it. And this is a long process. It takes typically a day or so to prepare a sample. There are no shortcuts. But when you've done that, you have got a very valuable specimen from which you can really learn an awful lot. And that's the end. So anybody questions on microscopy before we finish? Yes?
Yeah, you explained the mechanisms of the characteristic X-rays.
Yeah.
I wonder, why is that signal going to occur lower? Why doesn't
It doesn't occur lower, it just occurs through a bigger volume. Okay, because, I mean, the electron, you have a load of electrons coming in, and statistically, some of them, they undergo 3 or 4 interactions before they stop. And that gives you the total volume. And as I said at the beginning, you're actually generating all these signals everywhere. But it's only the X-rays that have got enough energy to get out again. Okay? Because the secondary electrons and the backscattered electrons have got so little energy that they can't get out of the sample again. On the other hand, the X-rays can. And that's why you pick up X-rays from that whole volume. Yeah? Well, you can see that kind of pear-shaped thing we drew here. That's kind of, so you can say roughly you've got a lateral resolution which is about half the depth resolution. And nowadays, people have got this kind of Monte Carlo simulation program. So if you really want to know exactly what's going on, you can put in the composition of your specimen. You can allow different electron trajectories, and you can actually plot that much more accurately. Oh, yeah, I mean, in cementitious materials, you're talking about, say, 1 micron lateral, say 2 microns in depth. Anybody else? Okay, so thank you very much for listening. I hope, in a nutshell, that brings you up to date with everything you should know about cements and concretes. I'm sure you've still got lots of questions that will come out over the next months and years, but hopefully you've got a little bit of an introduction there. So thank you.